All right, we are back here. It's Wednesday. We're going to continue with chapter 26, relating the electric potential to the electric field. Then we're going to get into conductors and sources of potential. So we're going to start off with a little bit of a review, maybe 10, 15 minutes. I know that this is kind of a difficult topic if you haven't seen this before. So I think, review can't hurt. If this is easy for you, you can tune me out and skip to part four. But we're going to start off with a little bit of a review. Homework 7, which is related to chapter 25, remember, is due Friday at 11:59 p.m. Homework 8 will be due the following Friday at 11:59 p.m. I forgot the p.m. Quiz 3 will be on Monday, and that will be concerning homework 7. And then we have our second unit exam on a week from Monday, which is the 29th during lecture, and that will cover chapters 22, 23, 25, and 26. So learning objectives, as always, are here. They'll mean more to you when you're done. So let's start off with a little bit of a review because I want to. This is really important that you understand what we covered in the last lecture. So remember, we've been discussing electric forces, electric fields, electric potentials for the last 2, 3 chapters. But this chapter really starts to tie them together and hopefully will help bridge some of these seemingly disparate concepts of the electric field and the electric potential. And so the main thing to remember here is that the electric field and the electric potential are simply two different ways of describing the same thing, okay? Namely, how source charges affect the space that other charges move through. And so the electric field and the potential, they're real. They're produced by these charges. They exist whether or not other charges are present to experience the effects. So these fields and this potential produced by the charges, they do alter space. They're real whether or not other charges are there to experience the effects or not. So we went over 2 ways last time in class for calculating electric field if you know the potential, and then we showed how to calculate the electric potential if we know the field. So in other words, if we know one, they're related, we can get the other. And so we started off, if you know how the electric field varies with position, along some path ds from 2 points, S1, S initial to S final, if we know how the direction and the magnitude of the electric field, and going from these 2 points, we simply integrate this. This is what's called a dot product, which is the magnitude of E times the magnitude of the displacement ds times the cosine of the angle between the motion ds and the electric field. And so if we know how the electric field varies along a given direction or a given path, we perform a mathematical integral, and that negative of that integral gives us the potential difference between the end point, S final, minus the initial point, S initial. Okay. So if we know the mathematical equation for the electric field, for example, a point charge, we can calculate the potential difference between 2 points by integrating this, plugging in E, the equation for the point charge, and then doing the integration. Okay. If you don't know a mathematical equation for E, the second way that we did last time is, suppose you have a graph of the electric field versus S, okay? The integral is just the area under the curve. And so we can get the potential difference as the negative of the area under the E versus S curve between 2 points. So these are both integration. This is what integration is. So If we know the electric field, we integrate it and we can get the potential difference. Now, there's certain cases like where if the electric field is a constant, we can pull it out of the integral. And in this case, it's easy to calculate a potential difference if E is a constant. And we derived in that case that the potential difference is just the electric field times the displacement, which would ds, which for a capacitor would be d. Electric field is constant. The potential difference is just ed, electric field times displacement. In terms of units, volts per meter times meters. Okay, so in this case, if E is constant, calculating the potential difference between 2 points is easy. It's just the product of the magnitude of the field times the distance between the 2 points. And so if you notice in this case, the electric field points from positive toward negative, and that is going from more positive potential to less positive or more negative. So in other words, the electric field points downhill in terms of potential, from higher potential toward lower potential. Okay, so this was how we went through last week. If you know the electric field, you can get the voltage or the potential. Couple main points here. Remember that the potential physically only potential differences matter, right? We can call any point we want V equals 0. It's only the difference in potential that matters. And another important point here is when the electric field acts on positive particles. So here's a positive charge Q naught, and the electric field, remember, points from positive to negative. And so the electric field is going to do positive work on a positive charge particle, right? Because the displacement will be in the same direction as the electric field, the electric force in this case. So positive work is done by the field on positively charged particles, okay? So he also talked about earlier in chapter 25 that if we know the potential at a given point, then the potential energy is just Q times V. V is just potential energy per charge. And we can apply conservation of energy on charged particles, right? Kinetic plus potential is a constant. And so we can relate the initial and the final speeds of particles moving in a potential difference using conservation of energy. And we saw in chapter 25 that if you have a large potential difference, V final minus V initial, we can accelerate charged particles to very high speeds. And this has a lot of applications in terms of medicine, nuclear physics, and various technological examples, some mass spectrometers, for example. So we can apply conservation of energy. Now, if we go back to our equation here, and let's just, for simplicity, assume a constant force. I'm sorry. Suppose that the displacement is perpendicular to the electric field. So in other words, theta is equal to 90 degrees. Okay, so in other words, a charged particle is moving perpendicular to the electric field. Okay, what's the change in potential? Okay, if you plug in 90 degrees, cosine of 90 is 0. The integral of anything times 0 is 0, and delta V is equal to 0. So in other words, if charged particles move perpendicular to an electric field, their potential the change in their potential is 0. So in other words, no work is done on particles moving perpendicular to the field. And since the potential is constant if we move perpendicular to the field, these surfaces of constant V are called equipotentials. Equa meaning equal, potential is V. And so, since this is perpendicular to E, the electric field is always perpendicular to the surfaces of constant potential, or these equipotentials. And you can also see, we talked about last class, if you plug in theta equals 0, that the electric field points from higher potential to lower potential. Okay, this is analogous to gravity. Remember, gravity points downward toward the Earth, and that's from higher gravitational potential to lower. And so, in other words, the electric field points downhill in potential, okay, from higher potential to lower potential. So here's an example for a point charge. Remember the potential we derived relative to infinity. Remember the potential at r is infinity is 0. And so if you have a charge plus q, the potential due to the point charge is a constant times q over r. And so we see that for a point charge at the same r, meaning the same radial distance from the charge, the potential is the same everywhere at a given r. And that's basically the definition of a sphere. And so these equipotential surfaces for a point charge are spheres. At a given r, a sphere of radius r is the surface of all points that have the same potential. Okay? And then you go to a larger r here, and all of the points on this sphere have the same potential at a lower value than this potential closer, because r is bigger, potential is smaller. And so for point charges, these equipotential surfaces are spheres, and since we know that the electric field is perpendicular to the equipotentials, that means the electric field is perpendicular to these spheres, which means radially outward from the source charge. And so the electric field is radially outward. And in this case, it goes out because it's a positive charge, and that's going from higher potential toward lower potential. Okay. If we flip this around and made Q equal to minus Q, the equipotential, here it would be K times minus Q over R. The equipotentials are still spheres, but we would get progressively more negative in potential as R got smaller, and then the electric field would point inward from higher V toward lower V. So here's another picture basically showing that the electric field lines are perpendicular to these equipotential surfaces, and it points from higher potential to lower potential. So that's if we know if we know the electric field, we can get the potential. Okay, more often than not in practice, we will know the potential because it's easy to measure. And so if we know the potential everywhere, calculating the electric field along a given direction S from the potential is just obtained by differentiation. Okay, so it's the opposite direction, right? If we know electric field, we integrate to go to potential difference. If we know the potential difference, differentiation is used to get the electric field. And so if we know how V is changing, if we know the rate, how many volts per meter the electric field is changing along some direction S, we can calculate that component of the electric field through differentiation. And examples for point charges and charged spheres, remember the electric field is along the radial direction, and so therefore E will only have an R component in the radial direction, and we can get the electric field by differentiating the potential with respect to R. So, in other words, the rate at which the potential changes with radial distance is the negative of the electric field. Now, in other cases, we'll have electric field will have components along x, y, and z directions, and therefore Ex is just negative dV dx, Ey is just negative dV dy, and Ez is just negative dV dz. And if it has all three components, E has an x, a y, and a z component, then we put all these together, and this is what's called, this mathematical operator in front of V is what's called the gradient. In other words, E, the electric field, is the negative gradient of the potential. Okay, don't worry if you haven't covered gradient. Just remember that each component of the electric field is obtained by the derivative of V with respect to that coordinate. Okay. So we went through in the last class, depending on whether V is given as a graph of V versus position, or a mathematical function, or in terms of equipotentials, there's different ways in which you can calculate the electric field. So one example that we did in the last class is if you're given the functional form of V, we just take the mathematical derivative to get the electric field. A second example, let's do one here. Suppose we know we have a graph, a plot of how the potential V varies with x. And so here V is in volts, and here x is in centimeters. And so the derivative in this case is just the slope of the plot. So let's do an example. How does calculating the electric field component Ex somewhere between x is equal to 0 and 2 centimeters. In other words, we get the slope of this line, delta V over delta x, and the x component of E is just the negative of this slope. So let's do it here. Delta V is V final minus V initial, which is 50 minus a negative 50. So delta V is positive 100 volts in 2 centimeters. And so the field strength, the voltage increases by 100 volts in 2 centimeters. So the field strength is the negative of 100 volts divided by 2 centimeters, or it's equal to negative 50 volts per centimeter. It's just the slope of this line, and then taking the negative. If you want it in volts per meter, that's equal to negative 5,000 volts per meter. Okay. The minus sign here meaning that the x component of the electric field, it points in the negative x direction. So it has a magnitude of 5,000 volts per meter, and it points in the negative x direction. Okay, so let's try it now between, what is the electric field between 2 centimeters and 3 centimeters? Okay, well, it's just the negative of the slope. And so in this case, the slope is 0 minus 50 over 1. So the slope is negative 50 volts per centimeter. Okay, so the electric field is the negative of the slope, which means the electric field strength is 50 volts per centimeter. It's positive, so it points in the plus x direction. So on an exam, if you have a plot of voltage versus position along some direction, say the x direction, you should be able to take the slope at a given point, tack on a negative sign, and that gives you the electric field. Okay, you should be able to do that. That's the second way of getting E, is just given a graph. Okay, finally, the third way is we know that the equipotentials are points of constant voltage, constant potential, and we know that the electric field is perpendicular, and so we can get the change in the potential divided by the change in distance, and it's the negative of that. So a third way, we'll do an example in a minute, is, we did an example in the last classes from the equipotentials. So here's another example of how the equipotentials are perpendicular to the field. Okay, so here we have two electrodes. We have a spherical electrode and we have a plane electrode. And we know that the electric field outside of a sphere is along the radial direction. So these field lines are along the radial direction. Okay, the electric field is pointing inward, so that means this must be a negatively charged sphere. Remember, electric field points from positive to negative. So we've got a negatively charged sphere, okay? And so these electric field lines are radial, and we know the equipotentials are perpendicular to the field lines, which means the equipotentials of a charged sphere must be spheres. They must be the same shape as the electrode. So here the electric potentials, the equipotentials are spheres. Over here we recall from chapter 23 that the electric field, if you have a charged plane, is perpendicular to the plane, like one plate of a capacitor. So the electric field lines point straight out, perpendicular to the surface. And that again means that the electric field lines are parallel to the surface. And so for each electrode, the equipotentials take on the same shape as the surface, planes, spheres, okay? And this must be positively charged, this plane, because the electric field lines point from positive toward negative. Then you get in between here, the electric field's a little more complicated because it doesn't look like a sphere or a plane. It's being influenced by both, and it gets a little more complicated. But in general, then, the equipotentials for most, like a sphere and a plane, take on the shape of that surface. The other thing to notice here is that the field lines are more closely spaced at the sphere than they are at the plane. That means the electric field here is stronger at the sphere than at the plane. We'll get into why in a little bit. So you should be able to, if you know the equipotentials and you know the change in voltage and you know over what distance this occurs, then delta V over delta X, or whatever direction this is, gives you the X component of the electric field. So there's three different ways you should be able to get E if you know V, either by differentiation if you know the functional form of V, or the slope of the V versus S graph if you're given the graph, or from the equipotential surfaces if you know those. So you should be able to get the electric field using one of those three methods. Here again, I mean, at the risk of beating this to death, tune me out and skip to the next slide if you already know this, but so the electric field strength, remember, is just equal to delta V over delta S. That's the magnitude in volts per meter. It's the rate at which the potential is changing with distance. So that's the magnitude. Remember that E points from higher V to lower V. So the electric field points perpendicular to the equipotentials, and it points from higher V, in this case, toward lower V, right? Here's the potentials are more positive over here. Potentials are less positive over here. So the electric field points from it points downhill, more positive toward less positive. So we've kind of, like I said, we beat this to death a little bit, but I don't think a little review hurts. So let's do this example here, a graphical example. So suppose you have an electric field, and at each point we drew the electric field at each of these points in space. Okay, so for here, it's pointing to the right, but smaller magnitude. Over here at these points, it's pointing to the right, but bigger magnitude. And then over here, it's even bigger magnitude and pointing to the right. And so the question is, which set of equipotential surfaces matches the electric field? Okay, so we can rule out most of these. Why? Remember, the electric field points from higher potential toward lower potential. Okay, well, look at F here. This over here is lower potential, higher potential to the right. No, the electric field is not pointing from lower to higher. It should point higher to lower. So we can rule out F, okay? The electric field, if this were true, the electric field should be pointing to the right because it's higher potential here and it's lower potential here. So F can't be true, okay? Same with E. Remember, electric field has to point from higher to lower. Well, that's not true with E. It's not true with D, right? So we can rule out D, E, and F just because electric field is pointing to the left, and we know that the electric field should point from higher to lower potential. So F is gone, E is gone, and D is gone. So now we're left with A, B, and C as candidates. Well, what do we notice here? Well, the electric field is strongest to the right over here, and it's weakest to the left. Okay? Now, remember, the electric field is strongest where the equipotentials are closest together. So it must be it should be C. Sorry, I got to fix that. So in case A, the equipotentials are equally spaced, which would mean the electric field should be uniform, the same everywhere. Not true. Over here, the electric field would be the strongest over here because the equipotentials are closest together here, when in fact that's not true. The electric field is weakest over to the right, and so the answer must be C, right? The electric field does get strongest as we go over to the left, and the equipotentials get closer together. And so I've got to fix that. The answer should be C. So you should be able to solve conceptual problems like this on a quiz or an exam relating the equipotentials to the field. Okay. So one application of this that is going to become very important with electric circuits is called Kirchhoff's loop law. Okay. And so here we have a bunch of we have three equipotentials. We have a 20-volt equipotential, meaning all points on this curve are at 20 volts. All points on this curve are at 30 volts. And all points on this curve are at 40 volts. Okay? And suppose we have a beginning point 1 and we have an end point 2. And we want to calculate the work done by the force, the electrical force, in moving a charge from point 1 to point 2. Okay. Now remember that the work done is equal, the negative of the work done per charge is the potential difference. Okay. And recall from earlier that the work done by the electric field is independent of path. Okay. And so one example here, similar to gravity, is if you look at path 1 here. So suppose the charge rides this equipotential from point 1 to point A. Its potential difference is 0, right? Because it's going along the same potential. Now it goes from A to B. So in other words, it's going against the field. It's going from lower potential to higher potential. Okay? That's going from 20 volts to 30 volts, and so the work done there, the change in potential is plus 10 volts. Now it goes here, It goes from B to C. It's riding the same equipotential, so delta V is 0. No work is done there. And now it goes from C to point 2, and its potential increases from 30 to 40, or it increases by another 10. And so when we add all of these up, the change in the potential going from 1 to 2 is plus 20 volts. Okay. Since the work done on per unit charge is independent of path, if we look here, it's the same change in potential taking this path. We start at 1 and we go to point 2. Point D, potential goes from 20 to 40, so that's an increase of plus 20. It goes from D to 2, it's going along the same equipotential, so its change in potential from here is 0, and the total adds up to 20. So in other words, no matter which path a charged particle takes to go from point 1 to point 2, it takes the same amount of work to move the charge along either path. Okay. So what's one consequence of this? What's the change in potential, or how much work does it take to move the charge around the whole loop here? Okay, so let's look here. Suppose we want to go from 1 to A to B to C to 2 and then back to 1. Okay, so it's going to gain 20 volts of potential in going from 1 to 2, and then on the way back it's going to lose 20 volts of potential going from 40 back down to 20, and when it goes back to where it started, it's back at the same potential. So in other words, the change in the potential of a charge and going around a closed loop is 0. And this is what's called Kirchhoff's loop law, or some people call it Kirchhoff's voltage law. It means if you calculate all the changes, delta V, acting on a charge as it goes around a complete loop, they have to add up to 0. It has to start and end at the same potential. Okay, and all of this is it's a statement of conservation of energy, right? So remember, if you start and end at the same point, you're going to have the same potential energy. So delta U is 0, and therefore delta V, which is the potential per charge, must also be 0. So what this says is that 0 net work is done on a charge and going around a closed loop. Or in other words, delta V around a closed loop is 0. So let's do an example here, and we're going to get more into this. It becomes really important with circuits. So suppose that we hook up 4 car batteries, and each of these are a 12-volt battery. Okay, and we're going to hook them up in what's called series, and we're going to get more into this in a little bit. Series means we just daisy chain them together. So we hook the positive of the first up to the negative of the second, and then we hook the positive of the second up to the negative of the third, and the positive of the third to the negative of the fourth. Okay, now the batteries really can't do anything unless we hook them up to some circuit, right? Otherwise it's kind of useless. So let's hook them up to this charge controller here. So now we have a closed loop. We have a wire, right? So in other words, the electrons start off here. Electrons are going to go negative to positive. They're going to be accelerated for the positive terminal. Then they're going to continue to go through here. They're going to go negative to positive, and they're going to go over here, here, and they have a closed loop to go around. In other words, they have an electrical circuit, a closed loop, a closed path for current to flow. So if we apply Kirchhoff's voltage law here, and let's call this point 0 volts right here, the negative terminal of the first battery, we can call any place we want 0. So let's call this 0. So what's the potential after the first battery? Well, it's 0, and it gains 12 volts, so the potential at this point is 12 volts. Come here. Potential is going to gain another 12 volts as we go across the second battery. So it starts at 12, it's now at 24 volts. comes in here, it's going to gain another 12 volts. So now we're up to 36 volts, and then it's going to gain another 12 volts of potential energy and going across the fourth. And so at this point here, we are at 48 volts higher potential than at the terminal here, the negative terminal, the first. Okay, now Kirchhoff's voltage law says that, or Kirchhoff's loop law, as your author calls it, says if you go around a loop, the total voltage change is zero. So if we start at 48 volts here and we have to end up back at we started at zero, that means we're going to lose 48 volts going across this charge controller in order to end up at zero. And in fact, that's what happens. So in practice, these 4 batteries would be used to supply energy to some circuit which is going to use it. And so this could be any device which is going to use the 48 volts of voltage from the battery. So the gain in voltage of 48 volts across the battery is going to be lost by the as it goes through here. And so in other words, the total voltage difference has to add up to zero around a closed path. And that's what's called Kirchhoff's loop law, or Kirchhoff's voltage law. So here's an example, another example. Suppose you have a 3-volt battery here, and you hook something up to this. So this might be a battery, and we could hook up whatever circuit is going to use, whatever device is going to use this 3 volts from the battery. So what's the potential difference between point 1 and point 2? Okay, well, we know here that if we start at the negative and we go to the positive, the potential difference here is plus 3 volts. So we start negative, we go to the positive, we're at plus 3 volts. Going across here, we've got to lose the 3 volts because we have to end up back where we started. And so if we gain 3 volts going across the battery, we must lose 3 volts going across this point, this difference, 1 to 2. And so in other words, the potential difference between 1 and 2 must be 3 volts. And it must go more positive as 1 to less positive as 2. In other words, we must lose 3 volts in going from 1 to 2, so that if you add up all the voltage changes around the loop, you get 0. Plus 3 plus a negative 3 is equal to 0. So Kirchhoff's voltage law, or Kirchhoff's loop law, again as your author calls it, says that the voltage gains around an entire loop must add up to be 0. Okay? Whatever's gained across some is lost across another, but they all have to add up to be 0 because you have to start and end back where you start in terms of potential. So I think we're going to stop here, and we'll start with the conductors and electrostatic equilibrium tomorrow. Then we'll go on to the sources of voltage, and then finally, to end the chapter on most likely Monday, we'll get into capacitors. And so we're slowly building up to circuits here. So let's end with that, and we will see you tomorrow.